Okie doke. So additional practice with equation of motion question. Question 42 says a baseball is hit almost straight up into the air with a speed of 25 meters per second. Estimate how high it goes, how long it's in the air, and what factors make this an estimate, which is basically air resistance. So when we idealize a situation, meaning we don't take air resistance into account, we say that, let's say something is hit upward with a speed of 25 meters per second, it's going to go up to some height, and then it's going to speed up on its way down, and it'll be going 25 meters per second in the downward direction when it gets to the same height from which it is thrown. Air resistance, if we were to take it into account, the ball actually loses some energy as it goes, and so it wouldn't go to quite as high as we would calculate, and as it falls down would be going something less than 25 meters per second. But we do not take air resistance into account, so let's take a look. I think how high it goes. I solved up here. So how high does it go? I have a diagram. Notice how the arrows equal magnitude, different direction, indicating velocity. Here's our baseball player. And how high does it go? So I'm listing given information. Initial velocity in the vertical direction, 25 meters per second. Initial position in the vertical direction, 0. Height, meaning final position, right up here. We want to know that. And here, this given, or I'm sorry, it's not told to us, but it's implied information here is these we just have to know is that at the top of its flight, its velocity will be 0. So this is where we're interested in. We know its velocity will be 0. We also know or can assume we're on Earth, and so the acceleration due to gravity is negative 9.8 meters per second squared. So substituting in gives us this formula. Again, we're solving for the position here, and we solve, and I think I rounded this based on sig figs, 32 meters. Interesting. Okay, second part, how long is it in the air? So long in air. So I have a diagram indicating starting here and ending here. Given information, we're looking for time, t equals question mark. Initial velocity in the vertical direction, 25 meters per second. Acceleration, negative 9.8 meters per second squared, because we're on Earth. And then look at this. Final position and initial position are both 0. Starts here, ends here. So substituting in, we're using this equation, the one involving time. And again, we get this quadratic thing. 0 on one side. I have factored out a t from here and here. These two numbers give us the negative 4.9. And solving, either this is equal to 0 or this is equal to 0. So if that's equal to 0, subtract 25, divide by negative 4.9. And we end up with two values. So this would be the start, and this would be when it lands on the ground. 5 seconds in the air. That's pretty much a long time. Okay, I think we can do the next example. So 44, and here we have a basketball example. There's your physics teacher trying to have mad ups, which he doesn't. So 44, the best rebounders in basketball have a vertical leap, that is vertical movement of a fixed point on their body, meaning how high can they jump, of about 120 centimeters, aka 1.2 meters. So what's their initial launch speed, so initial vertical velocity, and how long are they in the air? So here's a diagram. Boing, jump. And so that means if they were to reach a height of 1.2 meters, the bottoms of their feet would be there. Here are their feet, and they're standing up tall. That's mad ups. Okay. And I think what we're interested in, yes, here is initial launch speed, initial vertical velocity. We know they gain a height of 1.2 meters. So let's see if we can translate that into some physics. Initial launch speed, so, excuse me, initial vertical velocity equals question mark. Final vertical velocity equals 0 meters per second. Again, we're using the fact that at the top, the apex of the flight, the vertical velocity is 0. That gives us additional information to help us figure this out. We assume we're on Earth, so acceleration is negative 9.8 meters per second squared. Initial position 0 meters and final position 1.2 meters. So notice this is all information related to vertical motion. Nothing side to side. Even though we use x for position, and I know that's a little funky, but you'll get used to it. So we're talking about vertical motion. Here's final height, final velocity, initial position. Substituting in, let's see, that doesn't work. Maybe this is my favorite formula, but unfortunately didn't get to use it this time. Okay, so final velocity, initial velocity, acceleration, displacement, and we're solving for the initial velocity. So solving this down, don't forget to take the square root, gives us something like 4.9 meters per second in the vertical direction. All right. And then we were asked, how long are they in the air? So for how long are they, your physics teacher with mad ups, in the air? So t equals question mark for from here to here. T equals question mark. Initial vertical velocity. Notice how I stole that number from what we just solved. I'm using that number from what we just solved. And notice all these decimal places I'm including because it is part of the calculation. It's not a final answer that we're reporting. Okay. Initial position, initial position, final position, because it lands back on the ground. The basketball player, and the basketball player is on Earth, so this is the acceleration due to gravity. Right. So we're solving for time. We have to use this formula that I love, the one involving time, 0, 0, etc. And again, this quadratic. So from these two terms, I am factoring out a t. We get t equals 0, and we get t equals 0.99, or 1 second. So t equals 1 second in the air. Mad ups. Alright, I think that's it we'll have another video explaining the rest of the questions. Good work.